Good morning and hello, everybody. Thank you all for joining us for today's METALCON Live. Today's presentation is It's All in the Air Flow, Ventilation, Insulation, and Energy Codes for Metal Buildings. Our speakers today are Sam Gray of Metallic Products and Bill Beals of Therm-All. We're excited to announce this session will also be presented at METALCON in person in October by both Sam and Bill. Be sure that you register today so you can see them live and in person. Speaking of registration is open now with hundreds of exhibitors, dozens of educational sessions, networking sessions, and so much more. Here at METALCON, we're pretty excited to announce two major things. The first of all being the triumphant return of the Architect's Experience with exclusive curated education, a private floor tour, special hours, and so much more. Be sure that you keep your eyes out because Bill Beals is also doing a presentation for the architects as well on air barriers. The second thing we're excited to announce is the Future Leaders Program at METALCON. This will include a dedicated networking session, special education, and it's free with your total experience, architect's experience, or exhibitor registration. All super exciting things that we're excited to bring to you. Before I kick things off and hand everything over to Bill and Sam, be sure to mark your calendars for the next METALCON Live on August 10th, featuring the new technologies of metal. If you happen to run into any technical issues, please feel free to shoot a message out or a chat out to METALCON Live, that's me, in the chat box. I'll be happy to answer any questions I can. Without further ado, I'm going to hand it over to Bill and Sam. Take it away, guys.
Hello, everyone. My name is Travis Wendt. I'm the owner and president of Metallic Products here in Houston. I just wanted to say a quick thank you for joining us here today. A lot of work and prep has been put into this presentation, and we're very excited about it. Thank you very much to METALCON Live for hosting us. Thank you to Bill and Therm-All for all the work you've done, and to Sam. And I just wanted to put a quick plug out there. As Kaylin mentioned, we will be doing this presentation live on the main stage of METALCON this October, but Therm-All and Metallic Products will also have booths there. So please stop by. That's why I wanted to put my face out there. So would love for everyone on the call to please stop by, shake a hand, put a name of the face. We're really looking forward to seeing you guys there. So without further ado, I'm going to introduce my Vice President of Operations, Samuel Gray. Take it away, Sam.
Thank you, Travis. Good morning and good afternoon, everyone, depending on where you're at. Thanks for joining us. Before we get started today, we've got to cover a couple administrative items. First one's going to be the best practices. I'll give you a few seconds to read through that.
Just a very brief thing here. If you guys don't mind just turning on your video if you can, Bailey.
Yeah, 1 second.
So you want to read it? There's no video? Oh my God. Is it working now?
No.
Do we have it working now?
Now we see the slide.
You see the slide?
Okay. All right, now we're up and running here. So let's go back to best practices real quick.
There we go. Thank you, guys.
All right, so a couple, like I was saying, a couple of admin slides we need to go through first before we get started. First one is the best practices. I believe that one was showing. Let's show that one more time so it's on the screen. Okay. Okay, next. So this is a AIA credited course. You can get credits. You can contact Kaylin and Bridget from Therm-All. They will help you get some information to get that credit. You can see the information here, and we'll cover more of this at the end of the presentation. This is going to be a 1-hour webinar to give you guys a better understanding of the symbiotic relationship between ventilation and insulation for metal buildings. We're also going to incorporate some additional insight into the latest energy code requirements that affect the metal building envelope. So with that, we're going to go through the objectives that we want to cover today. Next. So we're going to talk about the science behind hygrothermodynamics, and I'm really going to dumb this down. I'm going to make it very understandable to everyone, how it affects the building's longevity, calculating air exchanges, the factors to consider, and what to take into account when you're ordering. Ventilation helps a metal building's insulation performance. How does that affect it? And a history of commercial energy code, landscape, including the major governing councils that mandate today's codes. That's going to be a big topic Bill's covering. and then understanding metal building envelope requirements for the IECC 2018 Energy Code cycle. So lastly, the metal building insulation systems that meet the latest commercial energy code requirements, and then we're going to cover the basics of air leakage of the building envelope. So the question that is the impetus of this presentation is, why is ventilation an afterthought? Well, after reviewing the data and the results of a MBCA sub-meeting, we basically noticed a spike or increase of insurance claims with insulated buildings in regards to their condensation, in regards to condensation damage with water vapor damage through the building envelope. So in conjunction with that, we also noticed that there's a significant drop in building airflow designs and applications. And we arrived at the discovery that it appears that people within the industry think that you either ventilate a building or insulate, not both. And today I'm here to kind of prove to you that both of those elements work together in tandem, symbiotic relationship, right? That help with the building's longevity and the performance of it. So you're going to get the most bang for your buck incorporating these two systems together, okay? So moving in, before we get into the meat and potatoes of this presentation, we're going to cover some basics, some fundamentals, so you have a baseline to get the rest of the presentation. First thing we're going to cover is hygrothermal dynamics. That's the big science of it. And there at the bottom, I guess that's how you pronounce it if you're Egyptian. All right, so moving forward. All right, what is it? Relating to a combination of moisture and heat. Really simple. Hygro refers to water and thermal refers to heat. You can't manage a building's heat without also managing the moisture, okay? So if you increase the amount of insulation in a wall, you may also increase the risk of moisture and mold problems due to the dew point temperature within the cavity. So there's two elements of the hygrothermal dynamic property, and that is, first off, the properties, which is the study that include the vapor absorption of the isotherms, water vapor permeability, heat capacity, moisture-dependent thermal conductivity, and effusivity. Now, that's kind of a technical word there. That's just the rate at which material can absorb heat. Okay, so those are all factors that are incorporated. The analysis side of it is the information about the movement of moisture. So heat and airflow through your building's enclosed space, such as through the floors, the walls, assemblies, the building envelope, can provide moisture content within an assembly based on various conditions through simulations of interior and exterior conditions. Okay, so that's your baseline for understanding hygrothermal dynamics, but we'll get into a little bit better understanding as we go forward. So if I asked 10 people, how does a hot air balloon work, I think 2 would get it right. So if you know coming into this presentation that hot air rises, you probably could get a job at SpaceX. Pat yourself on the back, all right? So, but let's cover some 101 here. Hot air rises because it's less dense than the air surrounding it. Cooler air, meanwhile, is heavier. It sinks because gravity pulls it down on it more strongly. By warming the air inside the balloon, it becomes less dense than the surrounding cooling air, allowing the balloon to rise, okay? That's the force that's pushing it up. On the flip side, reducing the temperature of the air inside the balloon allows it to descend. So we get that kind of basic concept of the science of hot and cold air, right? So that's going to be the next part that flows into how does that principle work within a metal building. On this slide here, the intake element is a little bit too high up on the building. The lower the cooler air comes in, the better. Cool air will come in through the intakes of a building, whatever format that is, and will push the hot air up and out of the building. Basically, that's airflow in itself. That's helping your building breathe. As you see right here, this is the hot air escaping the ridge line of the building. Cool air comes in through the bottom of the building, forcing the hot air up and out. So the problem here, condensation. How do we thwart that? How do we combat it? Let's talk about what it is first, okay? Again, we're working off basics next. So it's a change in the state of water from a gas to a vapor form. We all learned this in 3rd grade science, right? Into a liquid form. Generally, it happens when vapor in warm air encounters a cool surface. Condensation does not need a solid surface to take place. It can occur when a warm pocket of water vapor encounters colder gases. So the dew point temperature and every temperature below it will turn moisture, which is your RH value, into a liquid. So for example here, the dew point temperature is 45 degrees. Any part within the assembly surface or within the insulation will change to a liquid. The same effect will occur at a 44 degree, 43 degree, and so on. So just like you see outside when you see clouds, that's one extreme meeting the other, and the result is condensation and or the cloud, okay? And when enough of it happens, that's how the water droplets form, and then you got rain. I know I'm keeping this very basic and fundamental, but it's going to help you get a baseline to retain all this higher end knowledge here. So now let's talk about how the relationship between ventilation and insulation is in fact symbiotic, that it works in tandem. Next. So in the past, the science associated with insulation and ventilation wasn't very well understood. The amount of insulation increased, ventilation needs also need to increase. Insulation and ventilation are in balance. The relatively warm, moist air dissipates outside the building through the vents, but that's an important element there that I just glossed over. We'll touch on that again. They have to be within balance of each other. If the balance favors insulation, however, warm, moist air becomes cooler as it nears the roof, and then it can't easily escape if there's no exhaust element. The air accumulates on the coldest surface, which is typically going to be your insulation, allowing mold to form, and if it's contaminated, the spaces provide a food source for other things you don't want in the building, like harmful bacteria, etc. Not only is this a potential health concern for people, but it also causes wood rot and degrades the insulation of the building. Okay, so how do we make this happen? How do we fix this problem? What has to happen in order to mitigate this as much as possible, maybe it can't be eliminated, it's going to be through temperature regulation, right? So you don't have those two extremes meeting each other and creating the condensation problem. No matter how astonishing a building looks, it's a waste if the inside is uninhabitable. So some of the pros of temperature regulation is especially true when the building's primary purpose is used for people. If there's a manufacturing inside this building or it's a warehouse, temperature control ranks among the most important parts of a building design. It needs to be taken into account. Okay. So some things that you can expect if you incorporate temperature regulation is people working in, if you don't have it, if they're uncomfortable, hot and cold environments often behave in an unsafe manner, and it's the ability to make decisions are compromised, and they perform manual tasks to a lesser degree. Expansion of building materials. This leads to misaligned joints during construction, usually with interiors. Some materials are affected more than others, and we'll go into that more here at the end of the slide. For the safety concern, heat causes workers to be less careful. Oftentimes they will wear less protective PPE and become drowsy due to heat fatigue, and that's when accidents can occur. Okay, so the temperature of a building is actually closely related to safety. And then about the materials, how that happens is when the temperature of steel structure rises, the atoms will vibrate. This process is called thermal agitation. That leads to an increase of intraatomic distances and causes an expansion. So be thinking about screws in paneling right here. The constant expanding and contracting is going to affect the tensile strength. Go back to that one slide. The tensile strength and the yield strength of the modules and the elasticity will decrease with increasing temperature. So fatigue properties are also affected by the temperature, and that could come down to the color of the panels on the outside of the building. Next. So a couple factors here that you want to take into account that affect temperature and is going to be your latitude, your altitude, your distance from the sea, your air mass circulation, warm and cold ocean currents, and then proprietary local aspects of the building site itself. Okay. So some key things that you can use to help your building breathe, or ideas, is whenever you're designing or evaluating a pre-existing building, you want to have a climate responsive architecture. So you can do a site analysis, and that can be done. There's lots of companies out there that do that. The layout of the building on the site and which end of the building is facing the sun, You need to consider windows and bay doors, things that let heat in and airflow if they're open or not. That'll change the equation. Build for a geographical reason. Are you in the mountains? Are you by the ocean? Are you in a mostly desert climate? And obviously designing for natural ventilation are comprised of two elements, which is your intake and exhaust. You obviously have to have both, and they need to be balanced between the two of them. Okay. So now we're going to get into a little bit of the technical side of this, but I made it really simple. In order to get that temperature regulation that we talked about, we now need to get into airflow exchanges, next slide, and how they're going to be calculated. Now let me start by saying, I'm going to take some time on this slide. Let me start by saying that this is a little bit of an art and science to solve this problem. How we do that is it's first going to just simply start with a conversation. And the first question we need to ask is what level of air quality is needed and or desired? And this can be done prior to the inception of designing a building or after you already have a building and ventilation wasn't taken into account and you want to assess what it is currently that you have to determine what you need to buy or what you need to change in order to get the end result that you want. This math and this process can be done both ways. So once you figured out the air quality that you need, and that's going to be proprietary to what you're doing inside the building. Are you drying tobacco leaves? Is it a manufacturing site? Are you producing liquid chlorine? Things like that. All those things are going to be factors that come into play here when you're deciding what the ACH needs to be, which is your air changes per hour. Now, so that's the next question. How many times do you need the air changed out in a building per hour? Now, you may have an OSHA mandate based off of your business model of what that needs to be, or it may simply be a comfortable factor, and that's going to be objective to you. So for training purposes here, we're going to stick with the example 4. You have a building and you want the ACH, air changes per hour, to be 4, which means the air inside gets completely gets changed out, freshed out 4 times in an hour. How many times does 4 go into 60? 60 minutes in an hour, right? So the answer to that is 15. For your exhaust element, remember how I told you there's 2 elements, exhaust and intake. We're going to talk about exhaust first. You're going to take the cubic feet of your building, okay? Divide that by 15, and that's going to give you your CFM. CFM is the cubic feet per minute. That's how much air you need to move, cubic feet per minute, in order to achieve the ACH that you want. Now that you have your CFM, you would use that and put that up against products on the market that have a certain, so this product would move a certain amount of CFM. You put that math up against it and you can determine what size and how many exhaust platforms you need to order, whatever that may be, in order to achieve the ACH that you want. Okay, are you still with me? So now that you've done that, the other element is intake. You can't have exhaust without an intake, okay? So the intake free area, which is going to need to be at the bottom, at the base of the building, because that's where all the cool air is at that's coming in. You take the intake free area, which basically assumes that you've deducted all of the obstructions. So if you have an opening with blades that open and close, you would have to subtract that obstruction in order to get the proper intake free area. That needs to basically equal and balance the exhaust CFM that you have for that building. So both intake and exhaust should be balanced. Here's what happens if it's not. If you have too much intake and not enough exhaust, you're not going to be getting not only the ACH that you want, you won't get that. You're not going to be, the building breathing won't be optimized, okay? And you basically are, in a sense, wasting money there. If you have the inverse of that, where you have more exhaust than you do intake, and those CFMs don't match, you're going to create a negative pressure element, okay? And that's what you don't want. That's 99% of the problems that we hear about is in regards to negative pressure. And you can't see it, and that's why it's hard to understand it. So let me speak to negative pressure a little bit. So it's a condition where air pressure is lower in one place in comparison to another. It can introduce contaminated air and air with high relative humidity in some climate zones. So for example, if you close part of the exhaust system on a 300-foot building on one side and they're open on the other side, you're going to create, in a sense, that negative pressure element will create a cyclone effect, and you're not going to get the ACH that you want, and it will actually bring weather into the building. That's when people think that their exhaust elements are leaking, when really they're not. They're pulling rain in from the building because they've ignored this principle of negative pressure. So how you can do that is, or how you can thwart that is, make sure that the exhaust and intake CFM elements are balanced with each other. Okay, if they're operating as designed and the exhaust elements are doing what they're supposed to be doing, it's not going to allow leaves, rain, snow to come in through your exhaust element, because it's going to be venting. Okay, it's going to have to combat that, and it won't beat it out. All right, next. So another thing that we see, these are just common misunderstandings and common field issues that we see, is conflicting air management systems. And how this happens is, people that didn't get this webinar, they don't understand the principles of negative pressure, hygrothermodynamics, how air works within the building itself, and how a building's supposed to properly breathe, right? So what we've seen in the past is huge fans right below the ridge line that basically is forcing air down to cool off workers. Well, if it's forcing air down, where's that air coming from? It's coming from the top of the ridge. And if you have an exhaust element above that, it's going to pull air through those vents, and that's why you're going to experience water coming in if it's raining. So ignoring these principles and not adjusting things or setting it up properly will cause problems with your building. Now, if you have also purge fans, exhaust fans that are pulling air that's inside the building and actually forcing it out, and you don't have enough intake to support that, that'll also cause you some problems. Like, I don't know if some of you have gone to a job site where there's a completed building and you literally can't get the door open because it's being sucked in. You have to put your foot up on the frame just to open up the door. That's negative pressure. That's the element that's going to be in place when you see that. So those are things that I wanted to bring to you guys to have a greater level of understanding of the science of airflow within a building and what affects it, and how this airflow can help regulate the temperature within a building so that your insulation is not compromised. It maintains its integrity, it has a longer life, and it's not going to get damaged. So with that, we're going to be moving on to more insulation considerations for metal building. We have Beals with Therm-All. He is the code man, and I'm going to turn things over to him. So Bill, go ahead and take it away. Give us a second.
All right. Thanks, Sam. Great. Very well done, actually. And my part of this will kind of play a lot into what you just said. So I'm going to share my screen here and make sure that everybody's looking at my screen and it's in the right mode. Everybody should be seeing mine.
We are seeing it, Bill. Perfect.
Okay. So I'm going to get started. For people that don't know me, Bill Beals with Therm-All. Been doing a lot of code presentations over the years as they've evolved, specifically for our industry, which is metal buildings. And a lot of this is kind of repeat stuff because some things in the code change every 3 years, some don't. So I'm going to kind of get us through the process of how this all works. A lot of people know ASHRAE as a standard, which is exactly what it is. It's the minimum standard of energy efficiency that's done in a 3-year cycle, just like the IECC. IECC is the energy code portion of the ICC, which is the International Code Council that has plumbing, fire, mechanicals, etc. So we focused more on the IECC and the ASHRAE 90.1 standard as far as envelopes go in our industry. The 3-year lag is between both of them, but ASHRAE typically will publish first, and IECC will do a publication, which is actually the code. And a lot of the reference data comes from ASHRAE, specifically to metal buildings, because the thermal performances and U values that we'll get into all come from submittal data that was done at ASHRAE. So there actually is a reference from IECC in part to the assemblies and the performance testings. So again, ASHRAE typically is not a code, it's just a minimum standard of energy efficiency. However, some states do adopt the ASHRAE standard as their energy code, which is perfectly fine, but IECC is more of a publication that has, the written language around a code more than just a standard and all the methodologies that are published in ASHRAE and how the programs actually work. So there's a couple of ways: the prescriptive approach, which is just that. We call it the cookbook approach, which all IECC codes and all ASHRAE standards have a table, and they'll publish U values for metal building roof, metal building walls, and all your fenestration. So it's pretty easy to just look at the table and say, I need to meet this, this, and this. And that's a prescriptive approach. And a lot of people think that's what they have to do, but you can actually do 3 choices. There's trade-off method, which is usually achieved through ComCheck. And there's whole building modeling, which is more of an open studio program that takes into account the whole building as it relates to its climate zone. So we mostly do the trade-off through ComCheck. So how ASHRAE is influenced through our industry is the Metal Building Manufacturers Association, and I'll say this now while it's there. Sam alluded to hydrothermal analysis. We actually have done quite a bit of that through the MBMA, and if it's not published yet, it soon will be. And it's a simulation, which is exactly what it is: indoor temperature, relative humidity, outdoor temperatures, relative humidities, the fiberglass and board insulation assemblies, and the vapor barrier perm rating, and how the moisture in certain times of year through that simulation will migrate in and out of the cavities. And right now we're, I believe, on our final 0.02 perm, and what the relationship of moisture is in these cavities based on that. And that comes into play in a part of the code called the weather resistive barriers, which is a part of the IBC. It's not the energy side, but I run into it quite a bit. And you have to have a weather resistive barrier to stop moisture from migrating into the cavity. And there's no exemption for metal building walls. The only exemption is, I believe it's an ASTM 331, which the metal building manufacturers can do with their panel. But it's a sealed panel and it is tested, and most pass, but you have to use all of what was tested under that E331 in that wall to be in compliance. The only other option, an exception to the rule, is hydrothermal analysis, which would prove that that moisture in that wall cavity will be introduced and mitigate itself out under normal conditions. So that's why we're looking more towards that side of it than the all metal building manufacturers just testing the wall panel. So the MBMA, National Insulation Association, and NAMA, which is the National Insulation Manufacturers Association, all through private testing through these companies, will submit data to ASHRAE for publication under metal building roof, metal building walls, and all other construction types are kind of done that way. But in our industry, specific to metal buildings, these are the 3 ways we do the hot box testing, computer modeling, and is it constructible, fair treatment with other constructions types. So it's pretty basic in what we do. And then everything, believe it or not, people think insulation, they think R value, but really a U value is more important than an R value. And it's the actual performance of an assembly over the performance of a material. So when you build a building and you put R19 in the roof and you squish it, and it comes down to the old U value was 0.065. That's a tested in place at 15.4. That's actually gone down over time. So as an owner or as a mechanical designer and as ventilation goes, you really want to know what is the overall performance of that assembly. So that's why U value of a roof and U value of a wall is the real performance that you need to pay attention to. And I got some tables coming up. The R value method that we have and the U value methods are two separate tables, but they're kind of the same thing. And I'll talk about that in a minute. So there's other parts of the code and the ASHRAE standards that come into play. And the alternate materials approach and paragraph has kind of expanded quite a bit beyond what it used to be. And what this means is you have all kinds of buildings, you have fabric buildings, you have construction types that are not part of the code itself. You have, brick and mortar, you have all your construction types that have been around for 100 years, but there's always other types of construction that are done that basically you have no test data to say that the envelope meets the code because this construction type is what it is. So it's more what I call intent, that you take that construction type, you design it with insulation and materials based on that design, and you submit it to the code official as to basically you're meeting the intent, but there's no U value testing to show that this is anything. And that code official either accepts that or he has to write a letter why he does not, stating the reason why the alternative is not approved. I've yet to see not one approved yet, but I do run into these types of constructions. So that paragraph used to be just one sentence saying you're meeting the intent of the code by doing this. So it's got a little more language there. The other is the U factor alternative. Every IECC code has had it and the ASHRAE standard has it. And it's the simplest example I can use is metal building wall under most IECC codes, say R13 fiberglass with R13 CI, continuous insulation. And that combination is what, under the prescriptive factor, was thought to be the only way to meet the actual code. And it's not. There's a U factor alternative, which says if you have a system that is tested per ASTM 1363 hotbox or simulated through thermal analysis based on hotbox testing, and you can back up the data that your U value is equal to or better than that prescribed in the R value table, then you're allowed to use that. But you have to have the test data to show that you are in compliance with the U value. So I talked about the R value table. This is what most people in an I code book will see: metal building roof R19 plus R11 LS, which is a liner system in a lot of your climate zones. And your metal building wall right here, R13 plus R6.5 CI, R13 plus R13 CI. These are R value tables based on what we know that systems test out at. So the liner system for metal building roof, and again, these are assumed standing seam roofs, thermal blocks with R3 minimum thermal block, and liner systems. There's others out there that are long tab. There's other variations of systems that are hot box tested and also meet the code. So the very next table in the I code is actually the U value, C402.1.4. So you look at metal building roof, U value 035, 035, all the way up to 6, and we go to 031, and then 7 and 8 go to 029. But if we look at metal building wall, we see climate zone 3 at 052. We see 079, 052. So back to that U factor alternative, what that's saying is if you have a system that has a U value of 0.052 or better, then you're allowed to use that under the U factor alternative, as opposed to, back to the R values table, the R value table. So there's lots of things that in the code that I've read for many, many years and try to get better understandings on. And this is one of the ones where a lot of architects just don't seem to understand what these methods are and why we're allowed to use them, but they're there. So heat and ventilation and IECC. So I'll start with heat. So as far as IECC goes, you have an option under the IECC actually to use the ASHRAE standard as a compliance path, as opposed to the IECC code. And it's, I believe, C401.2, which is called applications. And it said these commercial buildings shall meet one of the following. And the first choice is the ASHRAE standard. So as a designer, if you say, all right, I'm going out of IECC and I'm going to use the ASHRAE standard, you have to use the ASHRAE standard 2 years prior in publication. So I-18 code, any state using I-18, you'd have to use the ASHRAE 2016 standard as a compliance path as opposed to I-18. And there's a few reasons for that. There's a lot more calculation procedures that are outlined in Appendix A in ASHRAE specifically for metal buildings. And there's also what we call semi-heated space. So IECC does not have a semi-heated space specifically. They have low energy buildings, which is on the very low end of semi-heated space. And the lighting and heating requirements are below 3.4 BTUs per hour. And then there's a lighting requirement. So if you're under that in IECC, you're actually exempt. But ASHRAE has what's called semi-heated space. So in climate zones 1, 2, 3, 4, 5, you have so many BTUs per hour per square foot that are allowable. So for example, in climate zone 4 and 5, 15 BTUs per hour per square foot or under puts you into semi-heated space, in which your metal building envelope completely changes for what's required to meet the code and or by using ComCheck. It's a huge difference. But they're actually, so ASHRAE 16 has brought these numbers down. They're bringing the semi-heated space down in all climate zones. And it does affect the northern climates, I would say, the most, because I'm in Maine and a lot of our climate zones 4, 5, somewhat 6. When you go to this semi-heated space, or if you try to build a building, even though it's heated to that and you have a wet sprinkler system, it's more than likely going to freeze. Whereas the old BTU numbers were just at the point where you could actually get away with semi-heated space. So air barriers, I got some slides that we jump around on here, but make no mistake, as the codes have evolved, the language within the air barrier requirements has expanded quite a bit, because thermally we're kind of maxed out for metal buildings. And I think most other construction types, when you look at the U values and the systems of fiberglass board, whatever you want to use, we've kind of maxed out where we are as far as envelope goes. So the next thing was the air leakage, and it becomes mandatory to have an air barrier within the thermal envelope. And in some cases, whole building testing is required as per the ASTE E779. And you have a certain allowable leakage rates. And I'll get into this a little bit more, but there's a lot more language than just the testing of a building, and there are other choices. So the language used to be a couple of paragraphs. Now it's a continuous air barrier. The entire envelope shall be designed and constructed with a continuous air barrier. Exceptions are semi-heated spaces, which we talked about, and single white concrete buildings in climate zone 2B for some reason has always been in there. It has to have each component of the envelope has to be clearly identified, otherwise noted on the construction documents. The joints, intersections, penetrations, and basically all components must be noted. So some states are a little different, but up in New England here, we have some pretty good code officials that look at all this. So when you go to submit your drawings for a building permit, your drawings typically have to show all of this, as you have to designate the air barrier and show it on the drawings how all these different construction types interface. And whether you're blower door testing the building or not, these are still mandatory requirements. And the ComCheck reports are another part of that as far as the energy side goes. So I will tell you that this air barrier thing is not going to go away, and it all will circle back to the ventilation part, which Sam talked about, because now that we've talked about the envelope and the insulation and the air tightness, the air quality within a building comes into question. It's like, how are these buildings going to breathe? But I've got some, we'll get to that when we get to those slides. So the other part of the air barrier requirement are all your fenestration assemblies, the windows, sliding doors, swinging doors, skylights, all these have to be tested. And there's test procedures outlined for air leakage of all components. And on the prescriptive side of things, and even to meet the code, this one's a little more difficult, because if you don't blower door test the building, you have to use tested fenestrations, just as this table shows, to be in compliance. The only exception, believe it or not, is blower door testing. So if you built a building and you didn't use doors and windows that met this table, and the building passed, you're actually exempt from this table. And blower door testing, the MBMA has done it. I've got some test data that we've done over the years. It's not that hard to meet it, but I will tell you this. When it comes to air barriers within a building, the designer has three choices. He can choose materials option, he can choose assemblies option, or he can choose whole building. And if you choose whole building, that means the whole building is going to be blower door tested. And if it fails, you can't go back. You own it until it passes. And there's certain numbers under ASHRAE that you're allowed to get. You don't have to be at the 0.4. If you make corrections and you only get to a certain number, you're actually in compliance. So the other part of the code that is mandatory is called ventilation, and it's either natural or mechanical. I know Sam talked about natural as a big part of it. And in many climate zones, that's a great option. The mechanical side is a little more sophisticated. I'm not going to get into it other than to say Chapter 4, the International Mechanical Code, needs to be understood as you go into these buildings that are energy efficient, airtight, and we do not want moisture in the assemblies. So all assembly and U factors come from the ASHRAE. We talked about that. These tables contain basically generic assemblies because ASHRAE or IECC do not promote any proprietary or branded names. So here's what we call a banded liner system. In the code, it's referenced as a liner system. And that is the one that has the vapor barrier that covers all the purlins and a series of banding that holds it in place. We have a second layer cavity insulation that rolls out parallel to the purlins, typically uncompressed, and a second layer that goes over, and then your thermal blocks and your standing seam roof. So all of the R values in the bottom right are the tested U values that are published in ASHRAE. And as you can see, 037, 037, 031, 029, you get some pretty good performance out of these assemblies. But why this cross section's up, I'll point out to the hydrothermal analysis and what happens when moisture gets into these assemblies. So a vapor barrier is a barrier, nothing's 100%. These positive and negative pressures that Sam talked about play a huge role in the moisture content within these assemblies. It's not just moisture passing through the vapor barrier, it's a negative pressure pulling moist air from outside the building into the building, and that's usually contaminated moisture and can over time become a huge problem if not properly vented and changing the dynamic of how the moisture's got in there. So, and your thermal performance is less because any type of moisture as a liquid becomes a conductor of heat. Now, these buildings do cycle in and out of some moisture content, as do all other construction types. But again, you look at air tightness, thermal U values, the performance of all these systems, you start running into how do I make this building operate the best it can be? And that's with proper ventilation, zero pressures, no positive, no negative. These systems have been on the market quite a while. They perform and do a very good job in all construction types. This is an ice rink, and swimming pools, I'll tell you right now, could be a problem. But again, it comes back to what's this building going to be used for? And I heard Sam mention a couple, and I like to say swimming pools, because if somebody calls, say, hey, I'm building a swimming pool, what should I do? It's like you're calling the wrong person, because I'm not going to tell you to use a liner system. I'm not going to tell you use anything, because I've seen so many failures. Granite cutting buildings, all these need to be addressed by the proper engineering company and architects that can design and vent these buildings to perform the way they're supposed to perform. We have a lot of interruptions, so to speak, in the vapor barrier when we cover the purlins and go to liner systems. This shows most metal building manufacturers have a great flange brace detail now, which is either a knife plate or a double L that minimizes the penetration in the vapor barriers, which need to be 100% intact for it to perform. I've got a slide coming up that'll show you the difference of a vapor barrier with a 1-inch hole and a vapor barrier with nothing other than diffusion, which is what happens when gas as a water vapor goes through a vapor barrier. The walls by code, this is a perfect example of where we are at with metal buildings and fiberglass. The roof is a liner system, the wall is a liner system. The heating systems can be, as long as they're vented, these can perform quite well. Radiant heat is another one that we see a lot of, but I'll tell you this, if you got radiant heat, don't park your dump truck in there full of snow in the winter while it melts, because then you're going to call me and wonder why there's ice on your windows. Air leakage and infiltration. So I'll get into that a little bit. Air leakage is sometimes called infiltration, which is the unintentional or accidental introduction of outside air. Humid climates will have warm, moist air moving into the building envelope through leakage around passage doors, and in the winters can result in moisture in the envelope. Infiltration is caused by wind, stack effect, and mechanical equipment. I've got some slides that will explain exactly what that all mean. Wind creates positive pressure on the windward side, negative pressure on the leeward side, and how that reacts to either pushing outside air in or sucking inside air out. And this is why air leakage is very important on how a building is going to perform sitting in an industrial park in a real world situation. So in the mechanical equipment, it all moves air. So this is a real building. You'll have internal positive pressure acting in concert with external forces and internal as far as that goes. So when the wind goes up over a building, it has what creates what's called upward uplift. And it's suction pressure on the roof that lifts air within the cavity at some point out. So any moisture, sometimes it does get in your metal building envelope. There's some days it will exhaust itself just by the uplift pressure on the wind. But in the winter, all of your heat that you're trying to store, especially in Maine, you don't want that. So that's why this air barrier and air tightness has become a huge part of energy efficiency for all buildings. And then we talked about the wind. On the windward side, positive pressure. The leeward side is going to have the negative pressure. So you look at a metal building wall, we have that fully insulated with fiberglass here. And on the panels themselves, they're lat, but they're typically not sealed. So it's just a lat panel. And it will start pulling the heat out of that cavity that you've collected during the day, just based on how Mother Nature acts in a building that's in the real world. Stack effect is pretty simple. Warm air in the winter rises, cold air is introduced typically through air leakage down around the bottom. So we take a new building built to code with air barrier in there. We minimize that air that's coming in at the bottom, and then stack effect, again, what happens? You're going to start building a pressure cooker. So ventilation is everything on how these buildings need to and should operate. All right, so we talked a lot about the air barrier and the purposes, and uncontrolled leakage will result in increased energy use, and it all has to do with devil's in the details. Everything has to be detailed out. So I've got some pictures here that show some air barrier that we do for submission for code officials, and this would be a perfect example of a liner system. The white vapor barrier can be used as the air barrier, and that would have to be detailed out and shown on the drawings. We have other options where we can put air barriers within the assembly, and that would have to be detailed out and done exactly how this is done. We also do all the walls the same way. Again, the air barrier would be detailed and shown. All your transitions, all your floor to wall would have to be done. So technically, the way the code is written right now, this is what has to be submitted as a drawing for your air barrier design to meet the letter of the law. Whether or not you're going to blow or door test it is irrelevant at this point, because it's still there and has to be done. And again, you look at a well-designed building, a well air barrier building with all this insulation levels, things can go wrong real fast. And standing seam roofs, although watertight and perform very well, they're not airtight. So if you built a building with no insulation whatsoever and you were going to blow or door test it, you would realize your building could not get to pressure. So vapor barriers, fiberglass, air barriers, any combination thereof. So vapor barriers have three classes: class 1, class 2, class 3. And we are seeing some changes on that, which the hydrothermal analysis through the MBMA is going to help us out on. Metal buildings, most of the perm ratings on the vapor barriers we use are about a 0.02, which is as good as it gets in any industry, because metal buildings are prone they're not prone to condensation. All construction types are. Metal buildings just let you know real fast if you have a problem because there's nothing that will absorb the moisture. Steel, fiberglass does not absorb moisture. It just contains itself within the fibers themselves and the airspace. It doesn't actually absorb, nor does steel. So your drips are going to happen pretty quickly. So when you're using a vapor barrier as a air barrier, that's all fine, and as long as it's sealed and everything's good. But if you're using something different as an air barrier, like we've done, then you got to have what's called an air barrier, which has to be between 18 and 25 perms, which allows moisture, gas, air to pass through. So you're not trapping moisture within that assembly. So I talked about some buildings that we have tested just to see where we were at as an industry. And these were quite a few years ago. And fortunately, these were done just outside Boston in January. So we had inside warm temperatures, outside very cold temperatures, which allowed the thermography option to work quite well. So this thermography that you look on the left side here, that's basically a foundation wall covered by metal and sealed and insulated just like a normal building. And by looking at it inside, you think, wow, that's a very, very nice design. But if you look at the thermography, there's huge leaks of air around that corner and around that assembly. Same over in this corner, especially around those frames, because you got all your insulation is either compressed or coming together with voids. These can be basically the fail of a blower door tested building, which this one actually did fail until they made some modifications. We were also able to bring it back to a pass. So some of your other areas where you as a metal building guy build a building, do everything right, and the electrician comes in and tears all the insulation out behind the liner panel so he can get his electrical through and do his work, this is what happens. Huge leakages around other trades that were unexpected. So most of these can be repaired, but again, if you fail, you have to go back to these areas and make corrective actions until you pass or get to the number that is now allowable. Standard pass doors, I don't think it's any secret that you're going to have a lot of leakage around the doors and the frames themselves. That's why they have a table at which they must be tested. But even the tested doors, you're going to have leakage, but it's usually nowhere near enough to make a building fail. Even with 10 doors, there's not enough leakage there to make it kind of fail. So this is a table I was talking about as far as vapor barriers go. They have a 4x8 sheet of gypsum board here. So the perm rating is not like metal buildings, but if you take an interior temperature at 70 degrees Fahrenheit and a relative humidity at 40%, the natural diffusion, that gas going through that would equal to 1/3 of a cup of water. So you go to the right and you look at a 1 inch by 1 inch hole in that same thing with the same condition, that equals 30 quarts of water. So that's why I pointed out, as far as the air barrier goes and the vapor barrier goes, it's very important to make sure that all those seals are done, and those knife plates, the flange bracing, and everything that goes into the potential of poking a hole in these needs to be addressed. So I'm not sure where we're at on time here. I think we're good. And I know we were going to hang around and answer some questions, so I'm going to send this screen back to Caitlin, I hope. And I don't have a movie staff here like Sam and his guys, so it's just me.
That's a-okay. So I'm keeping an eye on this. And I'd love to hear a little bit more about, can you talk a little bit more about the banded liner systems versus long tab banded systems?
Yes.
Particularly their differences.
There are huge differences. So one of the biggest differences on a banded liner system, most of them offer what's called fall protection. And some have variations of that. Some are fall protected, some are not. Know the difference. Long tab banded systems are not fall protected in any way, nor have they ever been. And the other problem that you'll have with a long tab banded system, or can be a problem, although most of the manufacturers have changed this detail, is the bridging that goes in between the purlins that keep the purlins from rolling on one another. So long tab banded, you have to go up over that bridging and up over that bridging, and it compromises, number one, the appearance, and it compromises the thermal performance. But if you have and do what's called a top and bottom angle, TBA, that puts angle on the bottom of the purlins, angle on the top of the purlins, and eliminates this bridging that's in the purlin cavity. That's the way to do these and do them right. I have a lot of customers that do that and do it the right way, and they look phenomenal. The advantages, the purlins are exposed for other trades, the thermal performances are there, but just understand the difference.
Perfect. And just as I'm going here, if anyone has any questions, you can feel free to submit those either in the chat or in the Q&A section. Please feel free to submit any questions that you have for either of our two presenters, either Bill or Sam. I'll be happy to read them out to them. I do have a few more questions before we get to I do have a few more questions that have come through already before we jump into new ones. Did you by any chance, did you say that air barriers are mandatory at this point in time?
They are mandatory by IECC 2018, ASHRAE 2016. Yeah, so you have three choices. You have materials, you have assemblies, and you have whole building, and there you have to choose. But make no mistake in that the detailing and everything I showed is mandatory for permitting. You have to you have to show it, and you have to, even if you're not going to test the building, it all still has to be there and detailed out and labeled as such.
Awesome. Perfect. And are skylights now mandatory for testing as well?
Skylights are mandatory in two ways. Number one is a fenestration for testing and air leakage, and 3% of roof mandatory up to climate zone 6. Climate zone 6 and 7 are exempt, but technically skylights in climate zones 2, we'll call it 2 through 5, are mandatory as 3% of the roof. And I can tell you 90% of the buildings aren't doing it. That's another.
That's not terrifying as someone
Well,
who purchased homes now.
They're getting more and more exemptions, but it really comes down to lighting inside the building, showing that the lighting and the energy use is offsets the skylight requirements, but it's a very difficult path to choose. It's all done through whole building modeling, and open studio typically would be probably one of the ways. There's others, but you would have to have the best lighting guy in the industry to explain it to you.
Okay. I do have another question. Is there U value testing data for exposed fastener roofs?
Yes, they're not good. So I do a lot of comm checks for a lot of companies all over this country, and there's one of them that uses screw down roofs and liner systems all over the country. The liner system U value in the roof is 044. It's the only test listed in ASHRAE. It's the only test done other than your single and double or single layer stuff, which is basically an unheated building at that point. So when I have a roof that's screwed down with an R30 liner system, I'm at 044. I have to jump down to the walls and do a double layer wall to get to an 047 to trade that roof off. It becomes very difficult. So there is testing. It's in CommCheck in the drop downs, but it's very minimal at best. You have basically a 6-inch, 4-inch over the purlins and a liner system, and none of them are near code at this point.
Okay. Perfect. And let's talk about CommCheck. Is a CommCheck report mandatory?
No, it's not. It's actually showing that you're taking a trade-off method. So it's what we typically offer up in metal buildings, because we can add roof insulation and trade off wall insulation at a lower level. But by offering a CommCheck for a permit, that means you're taking the trade-off process. If you're not offering a CommCheck, then you're assumed to be following the prescriptive method, which means you must meet those tables in every single fenestration, skylight. Everything has to be the cookbook method. The R value tables, the U value tables, everything must be met, and you have to show that. So the reason I say CommCheck is not mandatory, it's not, but again, the prescriptive method can be very daunting, and there's not a lot of aluminum windows that meet these U values anymore. So that's why the CommCheck option is has done our industry well because of the trade-offs that it allows.
Okay. Those are all the questions I have received. If anyone has any questions, please feel free to submit them now. If there are no further questions, I'd like to thank everyone for joining us today. A special thank you to Bill, Travis, and Sam. Thank you all for being here today. And I do hope I get to see all of you guys at METALCON. All of our attendees, thank you for joining us. And I hope to get to see you at METALCON as well. Oh, awesome. I have a question about obtaining continuing education units, and I'm happy to answer that for you. So when you registered for this seminar, you should have gotten you should have had to have put in your AIA CEU number. We're going to look at that and see how many individuals stayed for a minimum of 45 minutes. At that point in time, we'll take those individuals that have been here for that 45-minute time span and send them into the AIA to receive your continuing education credits. You'll be receiving your certificates of attendance following that as well. You can absolutely find Travis at METALCON. He will be there in person as well. So I hope you get to meet him there. If there are no further questions, I will let this end. Thank you all for being here. Thanks again for a fantastic session and seminar. We will see you all soon. Bye, everyone.
Thank you, everybody. We appreciate it.